Hey, I'm Ram over at Google. I'm here to talk about Cuttlefish and how to develop kernels and bootloaders on it. Yeah, I've been here for a few years now. Before that, this is going to be a three-part talk. We'll talk about Cuttlefish and kernel and systems hacking. We'll talk about GBL afterwards, which is a generic Android bootloader, and then Paul's going to talk about how to debug it. For those of you who do not know, Cuttlefish is a Android emulator that's been around for a few years now. It enables systems developers to develop bootloader platform kernel changes, whatnot, and has been fairly tightly supported on virtual CI systems for a while. So you can run Google Cloud or run it on Google Cloud, AWS, whatever you want. It's also fairly configurable, so we've extended it to support wear configurations, automotive configurations, which is, I think, of interest for some of you. And yeah. So that pitch wouldn't be complete without reasons for why to use it. So we'll cover those. Virtual devices in the past were fairly non-extensible, which I believe Goldfish, the studio emulator, suffered from in the beginning. And so we strived to make it a little bit more portable. With regards to that, we're VirtIO compliant across all of our device implementations at this point. So, I mean, GPU was recently added, as was SND, but network and Wi-Fi and block have all been there for quite a while now. And because of that, we're supported across QEMU and CrossVM, which we maintain within Google. And then the automotive community has helped by rounding it out with QNX and OpenSynergy and whatnot. In terms of interactions, we have ADB, WebRTC in case you want to do UI interactions and whatnot, and that also supports multi-display if you have multi-display Android devices, and then Serial if you need to do any more fine-grained debugging. It's also used to test upstream Linux through the Android downstream fork, which we maintain at Google for the Android CI/CD pipeline. And then I believe Amit here has done some work to maintain with Lenoro's configuration, so I'm sure he'll talk about that. We support a number of architectures, and we run across a number of different cloud providers with or without GPU and emulation and whatnot. We also do have bootloader support, which was added a few years back. We specifically use U-boot. We're interested in bringing up Little Kernel, and we specifically, we're maybe 2 releases out of date, but we do have boot config ABB support, and fastboot. CTS VTS compliance is also present, so fairly robust for development purposes. Though, slides are a bit out of order, but I'll just talk about current events for the program at this point. Software-defined vehicle has been progressing along. Trout is being merged into Cuttlefish as of Android 15, so if you want to do that, you should just switch to Cuttlefish. With regards to developing your own CI, we've developed what we're calling a cloud Android orchestration program, and also a corresponding host orchestrator, which is just a on-device or on-host manager of multiple instances in case you want to test multi-device interactions. So pairing or Wi-Fi streaming between your 2 devices. There's also been this AOSP main migration, which has caused a bit of grief across the community, which I'll explain at least with respect to Cuttlefish. And then we've also brought up a Docker container to wrap all of our dependencies. So go back a slide now. With regards to the migration off of AOSP main, given that Cuttlefish is primarily or being used quite extensively within the automotive community and a number of our external partners, it doesn't make sense for us to maintain that posture with the rest of the platform. So we've split our dependencies and started moving them out of the platform where possible. The actual device implementation is staying on Android and will get released on a quarterly basis, but our launcher is moving to GitHub, and that's going to happen over the next 6 months. If you've built our Debian package, you will notice build times have blown up quite a bit, I do apologize for that. We are working on getting that down a bit, and I'm sure some of you have seen some bugs. Please report them to us. We're aware and working on it. And then given that the launcher and the device are no longer together, there needs to be some guarantee of compatibility. We've supported back about 3 versions at this point, up to Android 13, though I put Android 12 on that, which is an error. Yeah. In terms of development, you can grab said Debian package at that location, or at least build it from that GitHub link. We've got x86 and ARM64 host support. We're finally in Debian Experimental, thanks to Paul, so thank you, Paul. And yeah, you can get pre-builts over there. The Docker container containing all of our dependencies is also at that GitHub. And with regards to orchestration, if you would like to set up a local developer pool for your developers to mess around with Cuttlefish or do what they need, you can set up that orchestration server, plug in your keys, and have something that local developers within your network can use to, mess around with Cuttlefish or do their development or CI or whatnot. In terms of how to build Cuttlefish, that is what you do. In terms of how to build the kernel configuration for Cuttlefish and the bootloader config, that's what you do. And that's how you build our bootloader fork. If you would like to launch Cuttlefish with a non-default kernel, so the one you've built, that's command again, just take the resulting RAM disk, which contains all the kernel modules, and the actual image. That's for x86-64. That website link is how you would see the WebRTC port I mentioned earlier, and ADB would also be available through that. How to inject the bootloader and then get it to pause in the command line, or pause at the console before the jump so that you can mess around with it and make it boot something else. And that's how you launched Cuttlefish with GBL, or the EFI application, which is currently in development and not default yet. So I'll talk about EFI boot next. But what's next for Cuttlefish as a whole is EFI boot for working on Verdea Media for a number of the automotive consumers, and the OSP main migration. With regards to feature requests, just toss them there, or bugs or feedback or anything. And documentation is on sourceandroid.com. So, yeah. Okay. Second part of the talk. Generic Android bootloaders, big fancy name. It started about 2-ish years ago. I guess the program started about 2 years ago. I'll talk about that a bit, and how we've come to current day, and all the extra, In terms of this presentation, I'll mention what a bootloader is for us, which is the final stage in the boot chain, which loads the operating system along with any configuration data, and then jumps to it. With regards to what an Android bootloader is, it's all that plus some Android specifics, namely Android verified boot, which would be an analog to secure boot from Windows land, fast boot, and protected virtual or PVM firmware load, which is the bootloader component for loading protected VMs, and then also all of our Android specific configurations or parsing. So our boot image formats. Corresponding to those, there are a number of device functionalities that also need to be supported. So cryptography, graphics for fast boot, and T supports or T integrations for Trustonic, Qt, Opti, whatever your T is, and then hypervisor integrations if there are any. So I guess this would be a good time to talk about the motivations of the program. If we look at how the bootloader ecosystem for Android has been for the last 12, 13 years, we've had lots of duplication of implementations. So every year there will be some new fastboot command required of an OEM, or a new boot image, or a change to AVB, or protected PVM firmware load, etc. And that means that bootloader trees progress, but they're not necessarily updated by many OEMs, given the risks involved in updating your bootloader, which means that bootloaders fork and fork and fork, and so you just have thousands of copies of libavb floating around, or fastboot, and these all, well, fastboot not such a big vulnerability, but libavb just floating around unpatched is a rather large vector. It also makes software maintenance of all these devices extremely challenging, so it's a bit of a problem for the ecosystem, which we're not unaware of. And then, given that Android as a whole progresses, we have post-quantum crypto coming down the pipeline for Android 17, which will land in libavb and allow for, I forget the exact name of the encryption algorithm, but that support will be present. So again, libavb implementations will have to be updated everywhere. So we should probably talk about existing solutions to the problem. Upstream U-Boot, until a few years ago, had a port of Android Boot that Linaro contributed. Core Boot is a separate attempt to support a open source bootloader that everyone can support and maintain and contribute to, but it's open source and maybe quite a bit rigid in terms of its governance structure. UEFI did have an attempt at a similar solution called EFI Droid, which worked specifically on Qualcomm devices and was built outside of Android, so didn't quite have the same traction, and then was maintained just by a single developer. So that project has since ceased, unfortunately. Red Hat's recently started a No More Bootloader project, which is an attempt to wrap the kernel, the RAM disk, and a bit of configuration data into one blob, and effectively use that similar to U-Boot's environment file as a set of directions for the firmware to boot the operating system and get rid of the bootloader in the process. It's a little bit more rigid and doesn't allow for any gaps that said firmware implementation might not support. I expect that that would work for hardware devices that have a lot more support from Red Hat or other server manufacturers as this progresses, but not really relevant to Android yet. We're interested though. So I guess we should talk about requirements of the given all the pain points, we can come up with a set of requirements of what a solution might look like, which leads to the solution. For that, it would require an application with backwards compatibility across a variety of different bootloaders, with discoverable calls so you can probe to see what bits of support you actually need to interact with. And then primarily for us, closed source bootloader support, because we work with a number of OEMs that would like that. Which leads us to UEFI, which is widely used in the ecosystem. Linaro's contributed U-Boot support pretty much entirely. EDK2 has been around for quite a while, started by Intel and Windows way back when. Relatively stable. Revisions are more and more spaced out now. We had one recently. It supports discoverable calls. In parallel to, I think, Windows certification from way back when, Linaro and ARM are promulgating System Ready, which is an attempt to certify a board as compliant with various different payloads, and allows for an ease of use by purchasers to say, I want this piece of hardware because I know it will run my workload. At this point, and then, yeah, driver support for all the different block drivers or drivers of that you might want for your device. So that leads to GBL, which, let's see how to phrase it. It's a released version of Android Boot that is an EFI application and gets regularly patched by Android, would support all new Android requirements. And yeah, that's technical specifications for it. It's entirely Rust. We have targets for all three, but the interesting one for this group is ARM64. We've got libavb, boring SSL, all the relevant libraries built in. It is built with Bazel, which is a bit of a new one, and it's part of the Android common kernel tree now, so should be relatively easy for you all to grab if you develop that. it's also got Cuttlefish support and devboard support, which Amit will be talking about after this talk. In terms of the interfaces we require to use GBL, we'll group it into 2 or 3 categories. We'll start with the required bit. We need to load from disk, so block support, hashing for presumably all the crypto you need, RNG again to do your randomization, and also stack canaries and whatnot. Then also memory allocation to load said device, load the kernel and various artifacts, so DTB and RAM disk. And then the Android specific ones, OS configuration is highly recommended. It just tells it's our way of providing to the boot firmware the various configuration bits that we have derived from the boot artifacts, and then allows the firmware to do whatever they want to that those 3 sets before doing the boot. Slot and reason support, which is called AV slot, and then Android verified boot, which we require for GBL shipping devices. And next, recommended. So they're all primarily debug related, along with a bit more fine-tuned configuration for the Android specific bits. So Paul's going to talk about debug in the next presentation, and then for the Android specific parts, we have what's called image loading, which will allow you to fine-tune where the kernel, RAM disk, and DTB should be if you have a very finely tuned memory map, which most OEMs do. And then fast boot, which is technically optional, but everyone in the ecosystem uses. And then AVF if you have protected VM workloads on your device. So documentation, again, we have a large README, a bunch of docs describing all the protocols, and then if you have any questions or comments or requests, email addresses, and you can find the source on the Android common or kernel manifests. For what's coming up next, we're going to make an initial release of GBL in the coming month that is not at all required for adoption in the ecosystem, but is there just more of as a proof of concept of what we can do. In terms of upstreaming of all these protocols, we're talking with a number of you to upstream all of those to EDK2 and U-boot, and LK we will be doing on this side as well. Little kernel's UEFI support is very nascent. We've added it in the last year and brought it up on a number of devices, but we need to flesh out all of that support for to make it ship ready. In terms of the interface freeze, given the silicon schedule for all the OEMs, we're gonna freeze the interfaces for the next release in October. So if you have any requests, get them in by then. And then we are working to make sure it is a requirement for Android 17, but we should be in touch with all of you. Oh, and Paul's turn.
Yeah, thank you. So hello, I'm Paul, and I'm currently working for a Google lending team. So I'm about to talk about the debugging for the GBL. So yeah, so my work is to enhance the developer to debug experience with GBL and to enable partners to bring up GBL on their hardware more efficiently, and also make the developers more productive when adding new features. So let's take an example. So we have hello world.efi shipped together with the EDK2. So for example, if we want to debug that EFI, so the first thing is we need to load the symbol files. But you know, the EFI application is load dynamically, so the address sometimes changes. So actually, you can see there's 2 parameters here. It's the text address and data address, which is the data section address and the text section of the address, and it's dynamically. So the problem is how to get this address. So, and to look more detail into it, actually, the text address can be computed by the PE format of the EFI applications. So if we know the load address of the EFI application, then we can compute the test address and data address by the p-format, the offsets. So the actual problem is how to get the load address, which is always dynamically. And if you read the document of EDK2, you will know that on x86, the EDK2 will have a debug output on a special I/O port, like loading driver at the load address for hello world.efi. So then you can get the load address. And for U-boot, if you turn on some verbose output somewhere, then you can get the address too. And there are also another method, like in the EFI application, your own EFI application, you add a print. So you print your own load address before start. But this is not ideal. This all works, but just not ideal. So when we look into the UEFI spec, section 18, actually they have the standards for these. So we all know that the load address is stored in this table when the EFI loaded image protocol table. So if we can locate this table, then we can get the load address of any EFI applications. But to locate the table, the first step is we need to locate the EFI system table, which is a static table of all EFI supported systems. So let's take a scenario like if we have a hardware debugger connected to a board through the JTAG. So the hardware debugger can examine all the address of the all the memory address, all the memory data. So in the spec, we have a spatial table. There's a signature in the table. So the hardware debugger just search for all the memories to look for that signature. And the second field is the address. And it also has a CRC, so we can verify if it's really this structure. And this structure have to be aligned on a 4 megabyte boundaries. So the hardware debugger is search every 4 megabyte address to look for this structure. Then we can get the system table's address. And after we have the system table's address, so through this path, very, very long, and then we can finally get the EFI loaded image protocol table, and which we can have the load address of our EFI pages. But this looks very deep, but actually we only need, in real implementation, we only need to add 2 more tables to the UEFI system. So one is called the EFI debug image info table header, which is a configuration table. And another is EFI debug image info normal table, which has point to the EFI loaded image protocol, which has a load address. So as you can see that in here we have an update status. It's a volatile integer. Because in some small possibility, your hardware debugger might be just break into the code that generate these structures. So this status must be volatile to tell the hardware debugger we are not ready yet. And that's all. That's it. So in EDK2, this is actually already implemented, but some parts are missing, like the extension for GDB. The part is missing, so we already has a commit for that. So now in EDK2, it's already working, and in U-boot, we also have an implementation, but it's currently under review on the U-boot's mailing list. The current V2, there's still a lot of problems. So I think I will publish V3 next week. So if you are interested on review, And yeah, you can also join the discussions on the mailing list of U-Boot. And we have a demo tomorrow for the debug support. So you can ask me, but I have two demos. One is the GBL itself, and another is the GBL debug support. So yeah, you can ask me if you really want to see GBL or GBL debug. Just ask me. So I can show you how to do that. It's already work. Just we need to refine the code based on the review. Yes, thank you. So any questions?
For GBL, as a rather small OEM, is there a way to implement this on Qualcomm smartphones currently, or is this more of a it will come at some point in the future with new chipsets?
Ram, what's the difference between the trout and cuttlefish? Well, what does trout do?
Sorry. Trout is the automotive Android configuration that was released in Android 14, or sorry, Android 12 to 14 by the automotive team, and was maintained by them. They realized at some point that it wasn't really worth maintaining a separate fork, and so they merged in with us and went back to Cuttlefish. Yeah, it was a forked configuration, so you could. Paul and I did a great job. No questions. Cool. Oh, one more.
So you're enabling support for GBL in EDK2 and U-Boot, but is the intention that the Android's AOSP is going to maintain this support in EDK2 and U-Boot, or what's the plan there?
So we are working on. Sorry, work hasn't started, but we will be upstreaming the protocol implementations to EDK2 and U-Boot. We won't be maintaining forks with Android. So we would like the ecosystem to carry it forward.
Cool, thanks.
I think we can call it then.